welcome to this AAN Notes lecture. So just a little bit about AAN Notes and a bit about me as well. So we're AAN Notes, we've been around since 2007, and our goal and mission is just to offer lots of free resources to students like you to make sure you can thrive and make sure you can get the most out of your studies in VCE and kind of the years before and beyond that. We've been offering kind of these lectures like these for a couple of years now, since 2015, and it's really to make sure that you get as much support as possible and that you can get a bit of information about all these different topics to kind of stimulate your thinking and stimulate your learning. So what we have here is a couple of the things that AAN Notes offers, so make sure to check out the kind of AAN Notes website to have a look at all of these types of things. So we've got study notes and kind of newsletters and articles with lots of study tips and strategies to help you out, so make sure to check those out, and to have study notes which you can kind of base your own study off is really helpful, so that at least you have kind of a basis which you can have a look at. And make sure to check out all the videos and lectures like this to get a bit of insight into different topics and to learn about different topics. And then if you need a little asking a bit of questions and things like that on the discussion forums, definitely more than welcome, and you can kind of reach out to people across the state in terms of questions, and also tutors which monitor those discussion forums. So we'll get started now. So welcome to the 3-4 lecture, and we'll just talk about a couple little topics. So mainly what we'll be talking about today is the statistics and kind of hypothesis testing topic. And then we'll start talking about a little bit about complex numbers, circular functions, vectors, kinematics, and vector calculus. So we'll be covering stats in details and then doing a revision over all of those topics, because these topics are probably the ones which you don't see as much in other math subjects. So they're the ones which, if you're doing 2 math subjects at once, probably the ones that you want to revise over, or the ones that you might not have any pre-knowledge about in terms of before learning those topics. So it's important for us to kind of go through these and to kind of explore them a little bit in terms of just making sure to go through these topics. Please ask any questions you would like. Make sure to ask as many questions as possible, and because if you ask questions now, you can kind of clear up any misunderstandings or any questions that you might have. So please do ask questions. More than kind of welcome to ask questions. And kind of before we jump in, a little bit about me. So my name's Michelle. It's nice to meet you virtually, I guess. And I'm currently doing med right now, and I'm nearly finished, and even though I don't do as much kind of maths in the course now, I feel like all the kind of problem solving skills and all of the knowledge definitely does carry on, and it's one of those topics that kind of keeps in your brain forever in terms of the thinking about it. Yeah. Great, so let's just talk about kind of statistics. So what we'll be going through is linear combinations of random variables, a bit similar to methods, probability and sampling, but larger focus on kind of the sampling side of things, and we'll talk about what the difference between A of x and x a times is going to be. And then we'll talk about hypothesis testing. So it's one like most specialist topics, specialist in general as a subject, is one of those subjects which can be a bit hard to understand and kind of wrap your brain around in terms of all the concepts and all the things involved in it, but it can be one of the easiest ones to get marks on, because sometimes, especially for hypothesis testing, it's a very structured way that they ask questions, and they'll always ask questions in a similar type of way. So unless you make kind of a mistake somewhere, normally they're marks that you can pretty easily get, because it's quite consistent how they ask the questions, and once you see a few, you'll be able to identify how they ask those questions. So in hypothesis testing, we'll kind of be exploring null and alternative hypothesis, how we test those using p-values or confidence intervals and comparing them to levels of significance. And we'll talk through type 1 and type 2 errors, what they are and how to kind of work those out. Great, so this is kind of just a summary table of all the formulas that are involved here. So we have our statistics formulas, which we can see up here. So we have E of x ax plus b will equal to AEX plus B, and then we have our kind of formula for adding different variables together, as you can see there, and we square variables and kind of put them together as well. The given formulas are really important, so it's not really an explicitly taught part of the study design, but they do ask a lot of questions about given stuff, so making sure that you know about conditional probability, and making sure that you have a page in all your book listing all these formulas and kind of listing all these formulas and kind of different equation types. So you want to add variance, and then your standard deviation is just going to be found by the square rooting of those. In terms of means and kind of finding those, all you have to do is just times the variable by its probability, and it's the same thing for continuous, though you don't really do as much of that in specialist compared to methods. And then for normal, the mean is just going to equal to mu, and for your binomial, it's just going to equal to your number of trials times your probability. Inverse normal, always use this kind of standardized normal or the z-score, and then remember it's always to the left. So for those friends who have ClassPad, you can choose which direction or which tail your thing is coming from, so you can keep that in mind. For those who have TN Inspire, then it's always to the left, and you just need to remember that. Central limit theorem, that's the idea that you can kind of approximate samples via normal distribution if you're told to do so. Great, so let's kind of jump into linear combinations and what they are. So the devil of gambling kind of offers you two options to win money. So the first of which is you roll the dice once and you'll earn 2 times the number you roll, or you roll the dice twice and you earn the sum of the numbers you roll. So which game leads more to a more consistent outcome, i.e. less variability? So we want to kind of explore this a little bit. So in terms of what this is, right? So if we make x the variable we're dealing with, right? One of them, we have 2x, we roll the dice once but double it. Whereas the other one, we have x plus x, right? Because it's 2 individual rolls, but they just share the same distribution type. So we roll the dice twice and then add the numbers up that we roll. So the e of x here is going to be the same, right? So if we have e of 2x versus e of x, we'll have 2e of x, or e of x plus e of x, which also is just 2e of the x, right? But the story here is a little bit different if we talk about variability or variation. And the reasoning behind that is because if we have 2x, what we have to do is square the coefficient and then get that, so we'll end up with 4 var(x). Whereas if we have 2 variables being added together, we just plus them together, so we'll have var(x plus var(x), which works out to be 2 var(x). So therefore we can see from there that the second option would give us a more consistent outcome or lower variability. And the idea behind that is that if we do x once, but then scale it by a factor after, the key thing here is that if we scale it by a factor of after, then what we're going to do here is we're going to have y equals to ax, or the variable equals to an ax value. Compared to if we do something x times without scaling it, we just add the numbers together. So it's important whether you're doing the same thing a couple of times and then comparing what the overall outcome is, compared to if you do it once and then just use that once to estimate. And it kind of makes sense in terms of a sampling or kind of sample size type thing as well, because if you're doing something a number of times and you look at the overall result, that means you're going to get a more consistent outcome, right? Because you have a higher sample size or higher number of things you're basing the observation on. Whereas if you're looking at one thing and then kind of timesing it by whatever, what you're going to do is you're going to only be based on one thing. So the variability is going to be really large based on what that one outcomes thing is. So generally, if y equals to a of x, you'll get e of y equals to e of x, and then the variation of y will be a squared var of x, so you need to square it. So if it's x plus x plus x, instead you're just going to say it's just a multiplied by e of x and a multiplied your variation of x. So you can see that the means will be the same, but the variations are quite different. So make sure that you kind of can note what the differences are there. Good. So you need to be able to identify which one you're dealing with. So a of x or axxx. So VCA won't tell you, and it's one of those questions which VCA loves because people generally don't do well on. So just making sure you have a good idea of what you're dealing with here is really, really important. So whether you're dealing with the x plus x idea, or whether you're dealing with kind of the a of x idea. And so you want to decide if the question has individual components. So as in, is it one individual thing and I'm just having multiple one individual thing? And if that's the case, we want to add the variances together because they're separate variables. Or do we have something which we have one variable and then we're multiplying it a couple of times? And in that case, we'll just multiply it a couple of times. So find the probability of total x and y, and then find the probability that 3 components. So let's kind of go through an example on that idea and kind of explore what we might think here. So we have oranges which are grown on a citrus farm, and they have a mean mass of 204 grams with a standard deviation of 9 grams. Lemons grown on the same farm have a mean mass of 76 grams and a standard deviation of 3 grams. Okay, so the masses of the lemons are independent of the masses of the oranges. The mean mass and the standard deviation in grams, respectively, of 3 of these oranges and 2 of these lemons are. So I want you all to think to yourselves, which one do you think this is, and you can pop it in the chat if you want to as well, about which one you think this might be. Do you think it's that x plus x plus x situation, or do you think that it might be that situation where we have to times everything together? And the idea here is that we're going to be having a look at this and we're thinking, okay, so we have three what do they want? Yeah, 3 oranges and 2 lemons, right? So we have 3 individual oranges and 2 lemons. So we have 3 oranges which share the same distribution but are individual oranges, and 2 lemons which share the same distribution but individual lemons. So what we're going to get from there is that we'll first kind of define our 2 variables. So we'll have oranges is going to be normally distributed by 204, 9 squared, and this is something important to do for normal distribution, just to state what variable you're using and also tell them about what it's distributed by. It just helps it organize it better and also makes your working out cleaner. And lemons are normally distributed by 76 and 3 squared. So remember the part here is that it's going to be the standard deviation squared. So you must know that as well, that what you get here is the standard deviation squared, or the variance, instead of the standard deviation. You must be careful when you get something like this to make sure to square root it to actually get the standard deviation when you're putting it into your calculator. Good. So what we're going to get here is that it's going to be orange plus orange plus orange plus lemon, because they're individual things, right? They're just being plus together. So what we'll get is that E of x will equal to 3 E of O plus 2 E of L, which is going to just be that 3 times 204 plus 2 times 76, which is going to work out to be 764. And right away we can kind of rule out a couple of the options here, right? Because we can see already 3 of the options are not going to work. So we have a 50-50% chance of getting this correct. In terms of the variance of x, right, because it's individual things being added together, we'll just have var of O plus var of O plus var of O, which is just going to work out to be 3 var of O, then plus var of L plus var of L, so they're just plus 2 var of L, rather than 9 and 4 here. We're going to have 3 and 2 because it's individual things being added together. So then we'll have 3 times 9 squared, because that's our standard deviation. So 3 times 9 squared, which will be 3 times 81. And then we'll have 2 times 3 squared, which will be 18. So 2 times 18. Also 2 times 9, also 18. So you'll have 3 times your 81 plus 2 times 8, your 18. 2 times your 9, keep on saying 18, 2 times your 9, and that will all work out to be 261. But remember, this is your variance, so kind of what further you need to do from that is square root it, and you'll get that this is 3 root 29, which works out to be option A. Good. Okay, so let's try it with a different type of question now. So a farm grows these oranges and lemons. The oranges have a mean mass of 200 grams with a standard deviation of 5 grams, and lemons have a mean mass of 70 grams with a standard deviation of 3 grams. So Assuming that the masses for each of these are normally distributed, what is the probability occurring to 4 decimal places that a randomly selected orange will have at least 3 times the mass of a randomly selected lemon? So once again, we define our distribution. So orange is normally distributed by 205 squared, which is our standard deviation squared, and lemons are normally distributed by 73 squared. Okay, so now we have to consider what's going on, right? We note that the oranges will have at least 3 times the mass of a randomly selected lemon. So that means that we have 3 times the mass of one individual thing. So that means that instead of having, O plus O, L plus L plus L to talk about 3 times the masses, we're going to say that O is going to be bigger than 3L. Right? And we're going to find the probability that O minus 3L is bigger than 0, essentially. So we'll set X to be equal to orange minus 3L, because it wants to be 3 times the mass, right? So it's not the mass of 3 randomly selected oranges, it's 3 times the mass of a randomly selected orange. Selected lemon. So let me just say that one more time. So it's not the mass of 3 randomly selected lemons, it's the mass 3 times of a randomly selected lemon, and that's why we go O minus 3L rather than O minus L minus L minus L, or L1, L2, L3. So what we're going to do here is we're going to say E of X is going to equal to E of O minus 3E of L, which is going to be negative 10, right? Because that's going to be 200 minus 70 times 3. Good. Okay, so then the variation of X, and var of X has to be bigger than 0 because we need to square root it to get the standard deviation, will be the var of O plus 9 the var of L, because we went negative 3 squared. So it'll be 100, and so it'll be 5 squared, which is 25, plus 9 times 9 times 9, essentially 81, or 3 squared, which is all going to give you 106. So your new distribution is X is normally distributed by negative 10, 106. Now we want to find the probability that that is bigger than 0. So what we want to do is we can just calculate that to calculate kind of that distribution, or that X is greater than 0. So what we do is we pop that in and we'll get that it's 0.1657, which correlates with option C. Great. So let's talk about sample distributions now. So generally, if we look at one sample, X is normally distributed by mu, a standard deviation squared, or variance. If we want the sample distribution, we can take a sample of n and then calculate the mean, and then repeat for more samples of n. This will give us a sample mean distribution. So essentially, when we have multiple samples, right, what we're going to be looking for is the sample mean distribution, so what the mean of the samples will be. So it's the sample mean distribution, so the expected value is going to stay the same as the normal sample, and now the variance, or standard deviation, is going to be divided by n. So essentially your standard deviation here is going to actually be equivalent to your standard deviation of the sample with the line. It's going to be the old standard deviation over root n. And the reasoning behind that is when you're looking at your sample, you're going to, because you're comparing multiple samples, right? This has a larger variance to this one because you're comparing multiple things in this one compared to this one. Okay, so as the sample size gets bigger, the more accurate this will be, and that's because n will be getting bigger, and n and the standard deviation are kind of inversely proportional. Good. Alright, so let's have a go with a question like this. So the petrol consumption of a particular mode of car is normally distributed with a mean of 12 litres per 100 kilometres and a standard deviation of 2 litres per 100 kilometres. So the probability that the average petrol consumption of 16 such cars exceeds 13 litres per 100 kilometres is closest to. So see, we're taking 16 samples here, essentially 16 different cars to compare, right? So what we're going to do here is, the first thing what we want to do is figure out what's going on. So we figure out that the mean of the the variable when we're starting with has a mean of 12, so X is normally distributed by 12, and standard deviation of 2, so 2 squared for our variance bit. Great. So then what we want to do is figure out what the sample size is, and we can see that the sample size is going to be 16 here. Okay, next we want to figure out what probability we're looking for. So we're looking for the probability of the sample mean to be bigger than 13. Okay, so now we've kind of deconstructed our formula. Now we can kind of put this together. So we'll figure out what the mean of the sample is, and the mean of the sample will just equal to the mean of the distribution, which is 12. And then we want to figure out the standard deviation of the sample, and the standard deviation of the sample will equal to the standard deviation over root n. So that's going to be 2 over root 16, which is going to be working out to 2 over 4, or a half. So therefore, our distribution for our kind of our samples will be 12 and then 0.5 squared, or a half squared. And then we pop that into our calculator using norm CDF, and we'll get that value is going to equal to 0.0228, and that's going to be the value that's going to come out from here, and that's the probability that out of 16, kind of the mean average, the average of the 16 cars is 13. Good. All right. So kind of no matter what you're really doing, if binomial, uniform, continuous, whatever, if the sample size is big, then the sample distribution will approximate like a normal distribution. The thing is here, they will have to tell you that to use normal approximation. Sometimes they'll explicitly tell you not to use normal distribution, and that's what the central limit theorem is, that if you have the sample size which is big enough, you can approximate to normal distribution. But I would say it's safest not to use it until they tell you to. So for special methods, normally it's when n is bigger than 30, that's when we can use it. But I would say just if they will tell you to use it. They'll say use normal approximation or don't use normal approximation, depending on what type of thing that they want from you in the question. Okay. So if we have a large sample from a large population, we can say it's approximately normal, and they'll say kind of approximate to talk about the central limit theorem. So what they'll do is here, all you have to do is kind of use normal approximation here. So your mean will just equal to your kind of proportion in the sample in the first place, and then your standard deviation will equal to the population proportion minus your 1 minus your population proportion all over your n value, which is going to be equivalent to your standard error. And why this is because is essentially because if you think of what variance is, so if we think of variance, right, and now because the value you're going to be looking for is going to be your population proportion, or what you're going to try to be like finding in here is going to be your p hat, or your population is going to equal to your x over n, right? So your e of x will be equivalent to just your p, because remember, if you use binomial, it's going to be np to give you your mean, and therefore if you divide it by p, and you're going to just get p. So your variance of x, remember originally we would have said that this is kind of coming from the idea of like using binomial, because that's the other type that you use to figure out sampling. So your variance of x normally in binomial is np 1 minus p. And if you think of what's happening here, your variance of your p hat, or your sample, is going to equal to variance of your np, your variance of your x over n, right? And therefore what we're going to get from here is that this is going to equal to np 1 minus p, because that was your original variance, right? And then we're dividing this by n. So therefore what we're going to get here is that this is going to be divided by n squared, because we have a variable which we're doing here, right? And then so therefore what you're going to get here is that this is just going to equal to p 1 minus p over n, and then we're going to square root that to get the standard deviation, and that's how you get that value there. Good. So population proportion and standard error. Okay. So binomial, the normal approximation of the central limit theorem normally applies to the binomial, and you need n trials and p probability. So if the sample size is large enough, so np is not close to 1 or 2, eventually you'll get a normal looking distribution. So you can use mu equals to np, or standard deviation equals to np 1 minus p. And this is using just normal approximation in general compared to the other one, which is using stats, right? So the other one is when you're talking about kind of you're talking about trying to find the sample proportion, and that's why it's a little bit different. But this one, if they just explicitly ask you to use normal approximation, this is what it's going to look like. And this works as long as NP and N1 minus P are both greater than 5. Great, so let's talk about a question on this topic now. So what we'll have here is, so consider the random normal distribution with a probability density function of fx, 2x, 0. If the large number of samples of each 100 is taken from the distribution, then the distribution of the sample means will be approximately normal with a mean of 2/3 and standard deviation. So they want what the standard deviation is equal to. So first of all, let's have a look at the information. So it tells us that the n is 100, and it tells us that we want to find the standard deviation. So remember, the standard deviation is just going, because we're going from a normal distribution, from this type of distribution to something which is normal, right? And we're going to approximate it to be something normal. So it's going to equal to the standard deviation of the function over root n, which is going to equal the standard deviation of the function over root 100. And in order to find the standard deviation of the function, what we do here is, what we want to do is we want to kind of diff the function, right, to find what it is, and then kind of minus the mean squared. So we're minusing what the mean is squared to find what the variance is going to be here. So that's going to be from 1 to 0, 2x cubed dx minus 2 over 3 all squared will equal to a half minus 4/9. And that's going to give you variance is going to equal to 1 on 18 to get you where you need, right? Because that's going to be where you're looking for. And then what you're going to get from here is that your standard deviation will equal to root 2 on 6. So then this standard deviation will equal just to root 2 over 60 to get you the value that you want here. And that's essentially it. And then you'll pick that. That's going to be option A there. Okay, so what does the confidence interval mean? We can say, so if they ask you ever, like, what does this confidence interval mean and how do I represent it? It's essentially that we say with something percent certainty, depending on the confidence interval, that the population proportion falls between here and here. And this is often when you have the sample proportion and you're talking about what the population has. So if we have 100 samples and we do a 95% confidence interval, 95% of those intervals will actually contain the population proportion. The more certain, the higher confidence interval you are, the less useful, because there will be a larger range of values. So let's kind of talk about this formula in itself and try and break it down. So we can have a confidence interval kind of associated with each sample, and we have m, which is our margin of error, which is this full bit here. And how I like to think of confidence intervals is if you relate it back to the normal distribution, that's essentially what it is, because it's saying how many standard deviations this way and how many standard deviations that way. Because remember, this is just your standard deviation, right? That is your standard, your S is your standard deviation of your sample, and if we kind of, your S over kind of root n is going to be the standard deviation you're working with, right? So because that's your standard deviation, that's just saying that many standard deviations away from the mean. And your K value is going to just be determined by what your confidence interval is. And what you can use is just inverse normal to figure out what your K value is. And we'll talk about on the next slide about kind of approximations for it. But your X is going to just equal to your sample mean, N is going to be your sample size, and M is your margin of error. So what this tells you is this many standard deviations above and this many standard deviations below. If we go from that range to that range, that's where 95% or M% of the, or C% of the values is going to lie within. In terms of finding your K values, the ones I want you to remember is 90, 95, and 99. So it's 1.65, 1.96, and 2.58. Normally two decimal places is sufficient. So these are the three values that you must know for exam 1, or if any exam that you have which requires you memorize things. So it's quite similar to have these in, compared to your values for normal distribution, you'll have 0.68, 0.95, and 0.997 for 1, 2, and 3 standard deviations respectively. So it's important to know those 6 values. So the 6 values are 68% for 1 standard deviation, 95% for 2 standard deviations, and 99.7% for 3 standard deviations for normal distribution. And the other 3 values are going to be your K values for your confidence intervals, which are 1.65, 1.96, and 2.58. If you have a calculator, how you can find these is just popping this into kind of inverse normal of your calculator. And what you want to do is you want to figure out, so you remember our inverse normal goes from the left side, or if you have ClassPad, you can just kind of find what the middle part is. But essentially you want to figure out what the area here is going to be, and that gives you and enables you to find what that k value is. And you will get the negative k value here. Alternatively, you can find what this whole area here is and then just get the positive k value as well. It's up to you. And sometimes the questions will say use an integer multiple. In that case, normally it'll be for the 95%, and you'll just be using 2 in that circumstance. Okay, so we can use specific k values. So what you want to do is you want to rearrange your function, right? So from negative k to k, that's going to equal to the certain. So all it's saying is that a certain percentage of your area is going to fall between a certain number of standard deviations, and that's exactly what you're doing. So you're saying, okay, 95% of my values are going to fall within that standard, within from here to here, so our unknown k values. So therefore we can rearrange this to be 2 times z to the power of negative k, right? Z smaller than negative k is going to equal to 1 minus c over 100. So that's kind of the opposite of what we were trying to find. So therefore the PR of z smaller than k is just going to equal to a half of that. And then you're just going to do inverse normal to substitute this into a calculator to find what the k value is. Great, so let's kind of explore a question on this front. So a farmer grows peaches which are sold at a local market. The mass in grams of peaches produced in this farm is known to be normally distributed with a variance of 16. A bag of peaches is found to have a total of 2,625 grams. Based on this sample of 25 peaches, can calculate an approximate 95% confidence interval for the mean mass of all peaches produced on this farm using integer multiple. So we'll be using 2 here for our k because it's 95%, and they asked us to use an integer multiple. Great, so let's kind of break this question a little bit down. So we'll have our variance equals to 16, so therefore the standard deviation of the function is going to be 4. Then we'll know that that's going to be 25 peaches. So what that means is your kind of mean in this circumstance is going to be found via the overall mass divided by the number of peaches, which is going to be 2,625 divided by 25, which gives you 105. Next, you'll find that the n equals to 25 because of the 25 peaches, and your confidence level will be 95%, and therefore you'll be using k equals to 1.96, but you'll be using kind of k equals to 2 because they've asked you to use the integer multiple. Great. So then all we have to do is kind of collect that all in the formula. So we'll put in, so the confidence interval is our sample mean minus our k value times our standard deviation of the function plus, so 2, our mean value plus our k value times the standard deviation of our sample, right? So it'll be 105, 105, we can pop that in where the sample means are, times 2, which is our integer multiple of k, times 4 over root 25, and that's because 4 is the standard deviation of our overall distribution of our population, but it's not the standard deviation of our kind of sample, so it'll be 4 over root 25, which gives us our standard deviation of the sample, and we'll just repeat that there. So 4 on 5 is going to equal to 0.8, and so essentially you'll have 105 minus 1.6, right? So it will work out to be 103.4, and then we'll have 105 plus 1.6, which will work out to be 106.6 overall in terms of finding our value. And you can see that this would be in exam 1, and often they do questions like this where they kind of get you using integer, and that way you can kind of calculate the values you're supposed to. Okay, so in terms of hypothesis testing, what hypothesis testing is a way to talk about looking into claims, right? So many companies and many places will claim that they do a certain thing or have a certain average, and the idea of hypothesis testing is we're testing those claims. So why they are good questions to get marks on is because they're often structured the same way, and they can't go too funky with what they're doing just because it is a new topic that you're taught only this year. So, for example, a treatment is hypothesized to decrease the mean population size of a virus, and we want to determine whether this is true or false by taking with the sample and then comparing this probability of like this mean occurring in the context of that sample. So how it will be set up is that we will have like these two standard deviation. We'll have a setup for the function, which we'll talk about in another slide. But first of all, we need to talk about these ones. So remember the population standard deviation and the sample standard deviation. So the population standard deviation is just the standard deviation. So I'll kind of that, and then but the standard deviation of the sample, just remember it's going to be over root n, and make sure not to mix the two up because it can be really easy and then mess up your calculation significantly. Okay, so in terms of the steps of what we're doing, so in hypothesis testing, we assume the rule of guilty until proven otherwise. What that means is that we assume that the initial claim is true until we can prove that it's not true. So the null hypothesis is when there is no effect, and this is going to be the easiest mark you're going to get in all of your specialist exam, because they'll literally just ask you to state what the null and alternative hypothesis are, and all you have to do is literally just state mean equals to mean before, and mean is smaller than mean before. And the key thing here is that you're going to use the claim that they use. So you're going to get a sample mean as well, and you're not going to use that anywhere in your alternative or null hypothesis, right? You're only going to use that to predict whether it's bigger or smaller or just not equal to that value. So if the treatment is ineffective, so we'll say that we kind of assume that there is no effect, so that our mean before equals to mean after, and then our mean now is smaller than mean will be our alternative hypothesis. So i.e., and then so there's three different possibilities. It can be bigger, smaller than, or not equal to. And if it's just not equal to, this is kind of the two-tailed test, above or below. So I want you all to have a bit of a think about which one you think has a higher likelihood of believing the null hypothesis. And if you just have a bit of a think, so this will have 2 times the probability if we're actually finding it, right? Because we're looking at either end of the function. So therefore, it's more likely that this would have a higher p-value. So therefore, it's more likely that this one would be accepted, right? Because we wouldn't reject the null hypothesis because it's just a higher value. So this has a lesser likelihood of rejecting the null hypothesis compared to the one-tailed test. Great. So then we set up the level of significance. They'll tell us the level of significance, and they'll say, a significance of 0.05 or 0.02. And then what they want you to do is calculate the p-value. And the p-value is the probability of getting that extreme value whilst assuming the null value is correct. And that sounds a bit overly complicated, but essentially all you're doing is finding the probability of getting that value given that you have the original value being your mean and you have a standard deviation as well. You'll get a significance value, normally it's 0.05, and then if that p-value that we calculate is smaller than 0.05, we can state that therefore there is less than a 5% chance of getting kind of that value, and normally at that point we can say we're going to reject the null hypothesis because it's just too unlikely that a random sample that we picked is kind of in that 5% range. So what you will want to do is calculate the p-value is to set your x kind of your value in there. So that's going to be the value of the sample mean smaller than x, right? So you're going to have what's the probability that your sample mean is smaller than the sample mean that we found in our function, given that we know that that is the mean. So all we're going to do is set up in our calculator is just set that up for kind of putting that in, right? So you're just going to set that up for, if you think of like your norm CDF, you're going to just set it up for, what's the probability that you're going to go from negative infinity to your x value, given that your mean is equal to your mean 0, and then you have your standard deviation over root n as well, in terms of what you're going to put in. A couple different methods of calculating this. So how you can kind of compare whether it's going to be like rejecting or accepting the null hypothesis is, so the first thing is you define null and alternative. You find this for the standard normal distribution, and then you kind of calculate that from there, and you'll get the p-value from there. So you can just calculate what that is on the CDF, right? So you you're converting to a standard normal. Alternatively, you can just not convert to standard normal and just do it straight on your calculator, but you need to make sure to convert this to sample standard deviation, because you're thinking about what's happening in the sample rather than what's happening in the population here. The third method is a z-test. So what you want to do is choose stats, right, and then go to population standard deviation, and you want to use the population standard deviation in the circumstance because it automatically does the calculations for you. And then what you want to do is change the alternative hypothesis to whatever you need, and then click enter, and you're looking for the p-value, which gives you the value of p. Okay, if you want two tests, all you have to do is just times your value by 2, because if essentially what you're doing is, before what we were finding is the area here, and now we want to find the area that it could be above or below, so it's that far out above or below, and therefore you're just going to times the function by 2 to get you what you need there. You can see there. Good. Alright, so making inferences. So then what you do is, if your p-value is above a, you can say it's insufficient evidence to reject h0, or you can say just accept h0. And below a is going to be good evidence to reject h0, strong evidence, or very strong evidence, and this all depends on the percentages. So if it's more than 0.0, if it's less than 0.05, then it's going to be good. If it's kind of more than 0.01, it's going to be strong, and then if it's more than 0.01, it's going to be 0.01, it's going to be very strong. So those are kind of the cutoffs. I haven't really seen that used too much in exams, but it might be used in your SACs, so just kind of keep that in mind. Great. So let's kind of talk a bit about a summary of hypothesis testing. So it's all based on your kind of normal distribution and where that's going to be sitting, right? And what you're going to be thinking of is, one, what you're going to do is kind of set up your function of what you're doing and then kind of put that into there. So you're going to set up what your h0 and so your null and alternative hypothesis. You're going to find what your p-value is, right, according to using any of 3 of the methods, and then you're going to compare, and that's what you have to do in hypothesis testing. Great, so let's talk a little bit about type 1 and type 2 errors, and this is often somewhere that people might get tripped up a little bit in terms of questions. So there's always a tiny chance that the p-value is wrong due to just randomness. So when we find the p-value, what we're finding is the probability that we get such a small value given, or the value of that probability given that that is a thing. So what's the probability that we just get that due to random selection? So there's 2 types of errors in hypothesis testing, and that's h0 and h. So if we had h0 being true, right, but we actually rejected it because we thought, oh yeah, it's a bit too small, that's going to be a type 1 error, or false positive. And how I like to think of these is like the situation of firefighters, right? So in a false positive, you can smell the smoke, but there's actually no fire, and that's going to be a false positive because I think the fireman goes down the pole, right? So that's a false positive, and that's why you're going to have that false positive, and so you're rejecting h0 when it's true. And what this is going to be equivalent to is if you have a too high of significance value, and that's when that will occur, because the chance of doing that is going to just be dependent on your significance value. The higher it is, the more likely you're going to commit a type 1 error, because you might get a p-value of 0.05 exactly, and it might actually be, so your h0 might actually be true, but then because your significance value is 0.05, you're going to say, oh, I'm going to reject it, right? Whereas if you had a significance value of 0.01, you might not reject it for the same p-value. Type 2 errors is not rejecting h0 when it is false, and this comes up in the context of they will often do this type of question where they have you have you kind of accepting h0. So if you have a lower h0 value, right? So 0.01, and then let's say we get a p-value of 0.05 and we don't reject it, and they say, oh, if in reality, if we got this, what is the chance that we would still not reject it? And they kind of get you to find a cutoff value where you'll reject that, based on the significance value. And then what they do is they talk about, okay, what if this actually was false? What's the probability of still getting that value if our actual thing was larger than there? And that's how you normally get asked about type 2 errors if you want a quantitative kind of measure. So the idea is we want to reduce the chance of both errors. So type 1 is going to be the significance value. So you can reduce the chance of type 1 error by reducing the significance value, but this would also introduce the chance of a type 2 error, and that's just essentially because of the graph. So what you want to do is let the p-value equal to 0.05 and then solve for x to find what that is. And then type 2, it decreases with sample size. So the larger the sample size you have, the smaller the chance you're going to have kind of the type 2 error. So you want to find the inverse normal to find when the type 1 meets the type 2. So kind of this intersection here, right? And then what you're going to do is the probability of H0, given that H0 is false, to find what this type 2 error is. So you're kind of finding, like the intersection between these two, right? Of when you're going to actually start rejecting this value, right? So this is when you start rejecting that value, and you're trying to find what's the probability that actually happens in the context of what's happening here. So the H2 one would be that this is actually not true, but you haven't rejected it. So they want you to find the kind of the probability up to there, and that's where it's going to sit, right? Because that's the probability that it comes before it will actually be sitting there. Good. Okay. So let's have a go at doing this ourselves now. So we have a bank claim that the amount it lends for housing is normally distributed with a mean of 400,000 and a standard deviation of 30,000, right? So a consumer organization believes that the average loan amount is higher than the bank claims. So check this, a consumer organization examines a random sample of 25 loans and finds the mean sample to be 412,000. So write down two hypotheses. So this should be the part you like the most. So first of all, we're going to figure out the distribution of our function, or our kind of distribution, so our normal distribution. So x is normally distributed by 40,000 and standard deviation of 30,000 squared. Then we figure out what we're going to do. So our null hypothesis is going to be related to our 40,000, and our alternative hypothesis is going to be that it's larger because it says that's higher. So therefore we're going to do a one-tailed test. And our n value here is going to be 25 in terms of, because we looked at 25 loans. So therefore what we're going to do here is now set that up, and we can kind of identify what our sample mean is as well. So our null hypothesis is that our mean is going to equal to 400,000, and our alternative hypothesis is our mean is going to be bigger than 400,000. And you'll notice here that nowhere do we mention the kind of numbers of 412,000, because we are using that to calculate a probability rather than using that to say that it's actually that number. So that's what we're going to do here. Great. And they even explicitly mention that it's a one-tailed test. So then the bank claims, so we'll kind of move further on. The plot thickens to write down an expression for the p-value for this test and evaluate it correct to 4 decimal places. So once again, we can identify all those things that we identified before and now pop these things in. So what we want to do first is put out an expression for our p-value, right? So what that's going to be. So what that's going to be here is going to be equivalent to p is going to be the probability that x is bigger than 412, given that our mean is 400,000, right? So then we pop this into our calculator, and we're going to kind of put in that it's norm CDF of this function. And remember, we're going to be using a sample distribution here, so we need to make sure our standard deviation is 30,000 over root 25 squared rather than just 300,000, right? So we're going to work that out to be our normal distribution is going to be for our sample, because we've gone from calculating about the population to calculating about the sample, 400,000 and then 6,000 squared. So then that's going to just work out to be 0.0228 in terms of our function. Okay, so then we have to think about what we're going to do here. So are we going to reject it or not? And A is going to equal to 0.05, and because our 0.022288 was smaller than 0.05, that means that we do reject the null hypothesis because it's lower than that significance value. So we reject the null hypothesis, which is the bank's claim that their average loan amount is 400,000. So then they want us to find out what's the largest sample size to be observed before the bank's claim is rejected at the 5% significance. So we want the p-value to be 0.05, right? So we want it on that cusp of being rejected. So if we want it to be 0.05, what we need to do is do an inverse normal to figure out when that's going to be equal to. So we know that if x is bigger than x, where our mean is 400,000, we want that to be equal to 0.05. So we do an inverse normal into our function to find where that's going to be, and we'll get that out. If we kind of use our standard normal distribution, we'll get that our z is going to be greater than 1.644, and therefore we'll work out that x has to be greater than 409,870. And what you're going to do here is you're going to round down, because you need to make sure, so when you're kind of rounding here, you need to round down to the nearest, it's going to be to the nearest $10, but also you need to consider when you're going to round up or round down for this, because if you rounded down, what you're going to consider here is that it's going to be just kind of within that, like above the 0.05%, so that's good. But if you rounded up, that would actually become lower than the 0.05, so technically it would be rejected at that value. Good. So then what you're going to do is, often in questions like this, what further they'll ask is, that's going to be the kind of the value, and then what they're going to ask is, what is the probability that it is rejected? So what is the probability that it is rejected given that the actual mean equals to blah, right? And in that circumstance, so, or what's the probability that it's not rejected given that the actual mean is equal to blah? And what you're going to actually be finding is the probability that it's smaller than that value in the context of a different mean that they actually tell you is the true one. Okay, cool. So that's kind of probability and hypothesis testing all in a nutshell. So let's kind of explore a bit further about all of our other things here. So that's going to be our complex numbers and all of the other topics. So let's kind of whiz through this, not whiz through this, but go revise over this. So complex numbers are just a fancy way of using a fancy Cartesian plane, and what we want to do is we want to use it when we're like, what we want to do when we're using polar form is we'll often, like in division or multiplication or using de Moivre's theorem to find solutions, and that's when we want to use polar form, right? So polar form compared to Cartesian form. So Cartesian form gives you kind of a rise and a run, or like a latitude, longitude coordinate, whereas polar form tells you about a direction and then how far it's going in that direction. So it's just a different way to represent a point. So to convert from Cartesian to polar, all you need to do is equate it to r cis theta, and then what you're going to do is, because it's a direction and then an angle, so how you find the direction is going to be based on kind of where your function is going to be sitting. So if we think of kind of a graph, so we're thinking about a direction, we can see that's going to use, we'll kind of get like a Pythag triangle here, so it's just going to be x squared plus y squared. And then in terms of the angle, so we have, if we kind of use SOHCAHTOA to figure this out, we have the opposite and the adjacent, so we're going to use tan here, and the opposite is going to be y and the adjacent is going to be x, so we have tan theta will equal to y on x. And we must remember here about the restrictions on the argument. So what we can represent z as is I cos theta plus I sine theta, or in short, kind of cis, right? So C, I, S. And super important that you must remember the domain of these, that arg, so capital arg is going to be between negative pi to pi. Remember, it goes to negative pi but does not include negative pi, but it goes and includes pi. So that's one thing you have to remember in terms of finding solutions. If you want to multiply and divide, often it's easiest just to use polar for this. You can use just the Cartesian form, but often it's just a bit grosser and a bit uglier. So what you want to do is, if you have two things being multiplied together, what you want to do in multiplication is just times together the distances and then add the angles. And how this actually comes about is just from the addition of angle formulas. And then here, if you want to kind of divide the two functions, you're going to just divide the r components and then minus those components from each other. And the key thing here is just to make sure that you know how to prove these as well, because it's something that they can ask you to do, kind of the logic and proof topic. The conjugate of this is going to be r cis negative theta, and that's because cos negative theta is just going to equal to cos theta, because of the quadrants, because it's in the fourth quadrant, whereas sine negative theta is going to equal to negative sine. So that gives you your kind of conjugate, or just kind of negates your imaginary component whilst keeping your real component the same. Good. So if you want the argument of the angle, it's just of two things being multiplied together, it's just going to be the arguments added together, and then if you wanted to minus them, it would just be minus each other. In terms of the reciprocal of that to the power of -1, or 1 on z, it's going to just equal to 1 on r and then cis negative theta, right? Because it's essentially just going to be 1 over z, which is going to be the same as having a function which is just going to be cis 0, right? Because that's cis 0 is equivalent to 1 over z, so it's going to be the same as having 1 divided by r, because there's no r component to this, and 0 minus theta, or just negative theta. Good. Alright, so De Moivre's theorem, it's the theorem that we use to find the nth root of a complex number, and the number of roots it will be directly related to what power it is. So if it's to the power of 2, you'll have 2 roots. If it's to the power of 3, you'll have 3 roots, etc., etc. So it will have n solutions for nth roots around the circle, and they will be evenly distributed around the circle. And they must be in polar form and in the argument of negative pi to pi, so it must fall within there. So the De Moivre's theorem states that Zn equals Rn cis n theta, and that's where kind of our formula comes from. So we can see here that we have Z1, Z2, Z3, and they're evenly distributed around the circle. The key thing here is that they might not have the same R value, and that's just because of kind of when you square it and when you put it together. They might not always have the same R value that it's based on, because it wants the distance to the circle to be the same, and evidently the distance kind of going this way, and if it was just flat would be a little bit different. But just keep in mind that it might not always look like it's going on the same axis, but it will always be evenly distributed. So if it has 3 solutions, it will always be the same number, so it will always have 2 pi and 3 between the solutions, and that's a key thing about them. And you can see here as well, evenly distributed, 90 degrees between all solutions. Alright, so how you solve using De Moivre's is you just need to equate the R values and the kind of angle values. So what you want to do is write both sides in the form of r of Zn equals to Rn to the cis n theta. So you write that as your Z thing, and then you convert your complex number into polar form. So you're converting both into polar form and then just equating them. So you'll have Rn equals to the magnitude of the polar thing that you're finding, and then you just solve for that, right? R is always bigger than 0, so you can kind of use that to your advantage, and then you'll have n argument equals to your arc, right? And then n argument, you're just going to plus or minus your angles to get, you can plus or minus like kind of the amount you get there. Alternatively, you can just plus 2 pi n and kind of solve it like a general solution, and then you're just going to be dividing by n to get you, or let's say 2 pi k rather than n, to make sure it doesn't cancel out. So then you'll just be you'll divide your whole function by n, so including your 2 pi part, so you'll get this is plus 2 pi n, and then you just plus or minus 2 pi until you get all the values you need. And how you'll know what the values you need is that all the kind of angles will have to fit between negative pi to pi, and then you can convert to Cartesian if the equation asks you to do so. Okay, so in terms of complex conjugate root theorem, this is the thing that helps us do a bit of solving. And if all the coefficients are real, what that means is that if there is one complex root, there must be another complex root. And that kind of makes sense, because if there's no complex numbers in our equation, that will mean that there needs to be kind of a dops of some sort to get rid of that complex number. So any complex number which is a root of a function which has real coefficients must have a pair. So let's say we have something like this. We have z cubed plus 8z squared plus 25z plus 26, and we have a solution of z minus 2, right? So if we kind of put this in and try and find out what's going on here, or if we try to like do essentially a bit of short division here, so you can kind of put that in. So we'll have 1, 8, 25, and 26. So we can put that in and we'll have that this is going to equal to 1. So we'll have 2 here, and then 10, right? And then we'll put that in, so we'll have 20. And then we'll kind of divide that further. So we'll have that that's going to be 20. So we'll have those being plus together to get us what we want. So we'll have that this is going to be 40 here, right? And then we'll have that this being plus by that, we'll have 80, so we'll have 106 as our remainder. And then all we have to do in terms of simplification is write that bit on top of our denominator and have the rest as kind of a function by itself. But if we kind of substitute this solution, and I think this should be probably -2 to get a solution, so I'm just thinking, so that's -8, let's try -2 as a solution. So I think it should be -2 as a solution. So and try that. So we'll have -8 and then plus essentially 32 minus 50 plus 26, right? So we can make sure that's true. So we'll have that this is, yeah, so that will be 58, and that will be 58 as well. So let's try do that again, take 2, using -2 instead. So if we want to simplify that, so we'll do -2 here, we'll put do our short division, so we'll have 1, 8, 25, and 26. So when we put that in, we'll get this as 1, we'll have -2 here, so we'll have 6, which is -12, right? And then we'll have 13 here, so we'll have -26, and that's going to equal to 0. So what that's going to simplify to overall is z plus 2, and then z squared plus 6z plus 13. And evidently you can tell with this one it's actually going to be we can tell that it's going to be we need complex numbers of some sort, because essentially if we did this, it would be 36 minus 4 times 13, which is going to be much bigger than your 36, so it's going to be negative. So all we have to do is just change this to be, we'll do kind of completing the square here. So we'll have z plus 3 all squared, right? And then it'll be minus 9 plus 13. So we'll have plus 4 here. And then all we have to do is change this into an imaginary number. So we'll have z plus 2, and then z plus 3 minus 2i, and then z plus 3 plus 2i to give us what the value we need there is. So you can see that essentially completing the square is the main part of it, and just solving as per normal and trying different conjugate roots. Great, so this is the kind of summary page for your formulas, and these are the ones for circular functions. So you have your double angle formulas here, and you use the angles, so the addition of angle formulas for cos, sine, tan, and then you'll have your double angle formulas here. I'd say cos is probably the one which is used most heavily, so make sure you know that and know that well. And sometimes you'll need something called the half angle formula, and essentially you just replace this with an angle you know, and then just solve from there. And we'll kind of do a question on that in a little bit, but just making sure that you are comfortable with all these formulas is really important. How I remember it is cos is always cos, sine for addition, and the sine is is the opposite. So if it was positive, it was negative, and it's negative, it's positive. Sine is always sine, cos, and the sine always comes before the cos because it's an addition of angle formulas for sine. So sine, cos, and the sine follows what the sine is. So sine goes to sine, so x in plus goes to plus, and minus goes to minus. And then your tan your top will always be the same sign and your bottom will always be the negative. And it's plus plus and then times times. Good. Okay, so let's try a question on this. So if we have, let's do these ones as well. So it's kind of like the other half of circular functions, which is the inverse functions, right? So we'll have y equals to a sine inverse bx minus c plus d, and that's kind of the generic form of it. And these are, for your like inverse circular functions, they're probably one of the easiest circular functions to graph, because all you have to do is just convert it to the domains and ranges, and then you just kind of do a dot dot and then just graph it from there. So how you figure out the domains is you undo. So you take the bracket, so whatever the bracket is, and because that all has to fit within a certain domain, so it all has to fit within negative pi to pi, right? Because that has to be squished within negative pi to pi to make sure all the inputs into our sine inverse function fit within negative pi to make sure it makes sense. Because remember, the maximum of a sine function is 1 and the minimum is negative 1. So all we have to do is undo it. So we'll have bx plus minus c equals negative 1 to 1. So we plus the c's on both sides and then we divide by b. So we'll get x belongs to c minus 1 over b and c plus 1 over b. With ranges, what we do is we build up. So there's a base range of what it could be, and then we add things to it to make it bigger, right? And it doesn't necessarily have to fit within a certain thing, because remember, our function is repeating over where it's going. So the range that we use for this is from negative pi on 2 to pi on 2. And that's because that's when it would equal to negative 1, and that's when it equals to 1. So we just do the transformations to it. So we'll have that this is going to be equivalent to multiplying by what we have. So you could say that this is like that y belongs to this, and then just add the stuff to it, or you can kind of rearrange and move everything onto the other side to make it bigger as well. So you'll have y minus d will equal to negative pi on 2 to pi on 2, then you times everything by a, you'll get negative pi a over 2 to pi a over 2, and then you add the d. So you can see that both of them have been altered in some sort or the other. And it's the same thing for your cos inverse and tan. So with your tan inverse, your domain doesn't really change, but your range is kind of built up in the same way, because it's kind of flipped on its side. So where the range is, it's going to be built up depending on what your values that you're adding or kind of subtracting there are going to be. Great, so let's talk a little bit about calculus and how we figure that out as well. So the calculus rules that you'll know and you'll love are the product quotient rules, and kind of a tip here is just use the product rule unless kind of stated that you have to use the quotient rule. I just personally don't really like the quotient rule very much, because you have to remember which one goes where, whereas with the product rule you don't, like, it doesn't really matter which order you do it in. And add examples to your book that are complex or tricky to do. These are the formulas which are found in your these are formulas which are used a lot, and some of these can be found in your bound reference, can be found in a formula sheet, but most of these aren't found in your formula sheet. So for example, this one is definitely found in your formula sheet, right? But the rest of them aren't really. So the main thing here is that if you want to do this one should be kind of one of the chain rules, so you can use this as your chain rule. It's just the function notation version of it. But the main thing here is I find this rule is probably the most helpful rule to work with, because that means, like, in terms of integration, it just makes your life so much easier, because if you can just recognize that the top is the derivative of a bottom, you automatically know it's a log, right? Which is helpful. If you want to diff anything which is not natural base, you just have to convert it to log e first. And for exponentials, you're going to use the fact that e log e ax is going to be equivalent to ax. And for the other one, you're just going to use the change of base rule for log. In terms of these, just be careful of the domains that you're working with. So sine inverse, cos inverse, and tan inverse. A key thing about this is for sine inverse and cos inverse, you're going to have 1 at the top. Whereas for tan inverse, if this was x over a, you're going to have a at the top. So you just need to remember that these only have 1 on the top, regardless of what a is. Whereas this one will have a at the top, and making sure that kind of corresponds to your a squared at the bottom. These kind of just come from the fact that if you diff them, right, you'll have, this just comes from the chain rule kind of combined with these functions. So you diff the inside, which gives you f of x, right? And the cosine, sine, and inverse, they're just negatives of each other. So you have negative f of x, and then you just square the f of x at the bottom, keeping the function the same. Okay, so in terms of implicit differentiation, this is the idea. You just, whenever you see y, you differentiate as per normal, but add a dy dx every time. And the tricky part about this comes when you have products which involve something like xy plus x squared y squared or something like that, you know. And the thing here is that when you're doing product rule on this, if you think of the first component, what we're doing, right? So let's just do something like, we want to anti-diff this, x squared plus y, x squared y squared, or just x y squared, is equal to 1. And so let's say we want to use implicit diff on this. The key thing here is that we want to do product rule, so we'll diff one, then keep the other. So if we diff x, we'll have 1 and keep the other, y squared. And we have not actually diffed the y here, so we do not need to add the dx dy. Whereas in the second part, we diff the other, which gives us 2y, and keep the 1, which is x. And we have diffed the y here, so that's why we need to do the dy dx at the back. And that equals to 1. And then you just solve for what that is. So that's really important, that in the product rule, even though it's actively involved in the product rule, when we diff the other function and don't diff the component with the y, we actually don't need to add the dy dx. Really important. Okay, so then in terms of concavity, in terms of like positive and negative points, so when the double derivative is positive, then it's local min. When the double derivative is negative, and that's a local max, and that's essentially because you want something which is really, really positive, really positive, and then essentially getting smaller, so that's when you're going to negative. And then you want something which was negative, and getting bigger, and that's where you're going to get that. Points of inflection are just in general when the double derivative is equal to 0. A stationary point of inflection is when the derivative also equals to 0. Related rates is a topic which they like to do a lot. It's just based on the chain rule, and all you have to use is dy dx is equivalent to dy dt times dt dx, and you just combine them together to get whatever rates or values you need. And the key thing here is they like to do a lot of shape stuff in here, so making sure that you have formulas for volumes of cones and cylinders and cubes and all of that is really important that you have on hand. Okay, integration by recognition. So this is when you step down in power. So if you sometimes you choose the wrong one to substitute, it's fine, just rub it out, do it again. So it's almost always the one which is like under another function or looks more complicated is the part you let u. So you let one component equal to u, and then you want to look for the component of the derivative as well, so the du dx, and then you want to rearrange so it looks like the other component. So then you substitute u and du dx into the original, and then you solve for u, and then you sub u back, and that's really it. Integration with trig, kind of quite similar to integration by substitution, except what you're going to do is you're going to substitute 1 equaling to sine and 1 equaling to cos. So if for any odd powers, you're going to split the odd power, so there's 1 with just the power of 1, that's by itself. And then if you have both even powers, what you're going to do, or if you have any component with sine squared plus cos squared, you're going to substitute that in and just replace it to get what you need. And then you let u equal the opposite of the trig power, so let u equal to the opposite of the odd power rather than the trig power. So the one which is the you want the one which is the loner to end up to be the derivative essentially, or to be something similar to the derivative. So you're going to try and get it until there's like one derivative which has nothing, like the component of sine or the component cos by itself. And then you solve as per normal. And if tan is odd, then you can convert it to sine over cos. So if you have any odd powers or all even powers, then you must kind of use these to help out. So it's just all based on the double angle formula it's just mainly based on the double angle formula for cos, so cos 2u, but can be also based on sine or tan as well. So just making sure you're comfortable and know what those mean is really important, because it just helps with the conversions. So cos squared equals to a half 1 plus cos 2x, sine squared equals to a half 1 minus cos 2x. If you have sine 2x, that's going to be equal to 2 sine cos x, 2 sine x cos x, which you can then convert to, like, say that was 2 sine x, sine squared x, cos squared x, or 4 sine squared x, cos squared x. You could then convert that to sine squared of 2x, right? Because that is sine squared of 2x, and then you can convert that into like 1 minus a half, 1 minus cos of 4x. So you can do like conversions after conversions as well. Okay, so integration by parts or recognition, this is kind of a newer part of the study design. So integration by parts has been around integration by recognition has been around for a while, but integration by parts is kind of a new type, spicy type thing. So just like the chain rule kind of goes with the integration by substitution, the product rule goes with the integration by parts. So it's based on this formula of f of g of x, and essentially what you're doing here is it's based on the formula that f g of x, right? When you diff it, it's going to give you f dash g of x plus g dash f of x, right? So then it kind of stands to reason that if we were to move this to the other side and we wanted the derivative of one of them, if we move that across and then anti-derived everything, we would get that f of x, g of x is going to be equivalent. So f of x, g dash of x, or anti-diffed would be equivalent to f of x, g of x minus your g dash of x, f of x, right? Because your derivative of this is equal to that. So if you anti-derive that would just revert to the original function. So the example of this is for things which have like x squared equals to log x squared log x, or 3x squared sine minus negative 1 2x, and so they're often functions which look quite complicated and kind of combine together. So the key steps here is what you want to do is you have to diff from, so you'll have these questions which you have a diff from the previous question. So there's kind of two types of questions here. So you'll have, this is like kind of the recognition type. So they'll say diff this, hence do that. And what you want to do is diff what you have, right? And then anti-diff the derivative you've just found, and then rearrange until you get what the question wants, and then simplify the right-hand side, because that will be the side which is messy. For the other type, where you're doing that one, what you want to choose one function to diff and one function to anti-diff, just like we saw kind of with this function here. We can see that we're going to have to anti-diff one of the functions and diff one of the functions, because it'll be in the form of fx g of x, right, or g dash of x. So what we'll be doing is we'll have to diff one of the functions to get our f dash of x, and we'll have to anti-diff the functions to get our g of x. So how we choose which function to be the diffing function is based on the acronym of LI8. So that stands for logs, inverse circular functions, algebraic, trig, and exponentials. And based on which one comes first in your lettering, that's going to be the one that you choose to diff. Because, for example, for this one, right? So we have a log, and we have an algebraic one. So our log is going to be the one that we choose to be our f of x, and our x squared is going to be the one that we choose to be our g dash of x. And then essentially what you want to do is you want to find your g of x, and you want to find your f dash of x in here, and then you just want to substitute into the formula and then just complete the right hand side as needed. Good. Alright, these are some formulas that kind of come up in your questions. For logs, just don't forget that it's modulus, so you just need to make sure to reject one of the answers. For methods now, they actually don't worry about the modulus. Okay, so these are kind of a bit of summaries. So if you want to use integration by substitution, you step down in powers from the denominator and numerator. The goal is to get u and du dx in your function and to get rid of x entirely. Almost always your denominator or your complex part is going to be u, and then you want to convert all the terminals to u as well, so that you can kind of directly substitute. And a linear substitution is just du dx equals to 1. So special cases, if you have a squared minus x squared, and what you want to use is x equals to a sine u, and x equals to a cos u, because then once you put that into there, you'll see that that's just going to be equivalent to just using the Pythag of kind of sine squared plus cos squared equals to 1. You'll get that it's going to just equal to a cos u or a sine u, and just equals the derivative, and you can kind of anti-diff from there. In terms of trig identities, always split the biggest power. So there's a loner, let u equal to the opposite of the loner, and then use trigs to reduce the other parts. And these are kind of the values for the even powers to help you do what you need to do. Integration by parts or recognition, just make sure you can either use this formula, and what you're going to do is integrate both sides and then kind of arrange what you desire to be the subject. So it will either be a two-part, so diff this, hence do that, or one-part question using the LIATE acronym to help you. And just remember with LIATE, you choose one to diff and choose one to integrate, and it's pretty intuitive normally which one you choose to diff, because it's often the one that cannot be integrated, like a log or inverse trig function. And then you integrate both sides, and you want to arrange which one you decide to be the subject. And note, even something just like log ex or sine inverse of x can still be one of these things, because you can make your other function just equal to x equals to 1, and that's fine. These are partial fractions, which you can use to help out to integrate your functions as well. Just remember how to find these rules and these rules which correspond. So these are a bit of like a puzzle, and you put them all together to figure out exactly which bits and bobs you have to put together to make your original equation. And then once you get it into one of these, they'll always go into a kind of tan inverse or a tan inverse or a log function. So these will normally turn into logs, and this one will turn into a tan, because you just kind of complete the square for the bottom part to make it into look like a tan function, and then you can go from there. Okay, so then talking a little bit about our differential equation. So one of the differential equations that is of a common application is Newton's law of cooling, and this uses this rule. You don't really have to remember this rule, but essentially it's just based on the rate of cooling will be dependent on what the temperature of the thing is and what the temperature of the outside part is. So you can memorize that and have, I would say these questions are mainly coming up in exam too, so it's something you want to have in your bound reference so that you have on hand. So if you kind of forget how to do these types of questions, at least you have a formula already on hand that you can directly substitute into. And this is kind of based on first principles. Good. Okay. This one is a special case which has been explicitly named in the study design this year, so try to memorize this at least to have this in your brain. And the key thing with this one is it's based on what the population is, and it's also based on a limiting factor as well. So often there's like number of prey, or there's a predator, or etc., and or the size of the enclosure, etc., and essentially that means that there's going to be a limiting population, that maximum population that's going to be able to get up to. So what it's going to be based on is it's going to be proportional to both the population and the limiting population as well. So what we're going to get from that is, if we want to kind of put that into a function, that's going to be the value that you eventually solve to get. And just make sure you have this in your bound reference to look at. So P is going to be the population, L is going to be the limiting population, i.e. the population you get when T approaches infinity, and K is the constant, which kind of changes based on the equation, and often the thing you'll be asked to find. And another thing that you want to note here is technically EC is also a constant, right? The constant of integration, and you don't need to find what C is. So let me say that one more time to make sure we know this. You don't actually need to find what C is. You can just find what e to the power of C is as well, because it's going to give you the same thing. You just substitute in a value, right? E to the power of C, you get C as like a really complicated log equation. You don't need that. Just need to find what e to the power of C is, and you'll be fine either way. Good. Alright, these are also another type of question that commonly gets asked and commonly causes a lot of headaches. So these are mixing problems. The key thing here is to figure out inflow versus outflow. So what you want to do is break it up into your two components. So you'll normally have a tank like this, and what I like to do is like draw out my tank. So I like to talk about my dx dt in and then my dx dt out. So the amount coming in per litre is going to be equivalent to your concentration, or your dx dv, or whatever variable you want to use, and then your flow will be your dv dt. And you multiply those two together to get the rate of change of your concentration, of your amount of salt over time, right? That's going to give you your in. And then you're going to do the same thing coming out, except now coming out, you want to figure out the concentration. And often you'll be given the variable, so Q, let's say, in this circumstance. And this thing will be the volume plus the change in the volume. So if you have 10 litres going in and then 10 litres coming out, no change in volume, right? But if you have 10 litres going in and 20 litres coming out, your volume is going to be decreasing 10 litres per the time or the minute that it's coming in. So that's going to determine what your bottom is, and then you just kind of times out by the flow out, and that's going to give you that. And then you just combine the two together to give you your equation. So if you give your initial conditions for the equation, you don't actually need this in the formula. You're just going to use it later on when they ask you to integrate it and figure out what the values are. And that's just because this is the initial things won't really make a difference, because this is telling you about the change in the volume, or sorry, the change in the amount of salt in time. And just remember that it's just going to be inflow minus outflow, and just consider them separately, and I find that's helpful. So if inflow equals to outflow, what that means is that you're going to have you will just have it over V, right? And if inflow doesn't equal to outflow, that means that you'll have to change the V kind of based on the bottom. So you want to draw the situation, inflow, outflow, kind of capacity of the tank. And then you want to define your inflow, outflow formulas. So that's going to be your concentration times your volume flow in, and then your concentration times your volume flow out. And they'll say something like they stir the tank to make sure that you're aware that the tank concentration is consistent throughout. Then you're going to have inflow minus outflow, and then you solve for Q being the subject. Great, so let's talk a little bit about slope fields. So what they are slope fields. So slope fields are essentially a gradient table kind of on steroids, right? They're just gradient tables with a lot of things going on with them. So they're just kind of extra powered up slope. They're extra powered up gradient fields for lots of things. So what you want to do is you look at your x and y axis for patterns, so positive, negative gradients, zero gradients, undefined gradients. Then you look at the question. So if you want dy, dx, you look for turning points and asymptote lines. So you're going to look for vertical lines, that's where the gradient is undefined. You're going to look for horizontal lines, that's when the gradient is zero. And you're going to look for positive and negative sections of the gradient. If you want the y graph, what you're going to do is just draw the curve on the slope field and then look at the shape, because the graph on your slope field is going to be your curve, not your actual dy, dx. So keep that in mind. Okay, Euler's method. This is the formula. Please just have it in your noggin in terms of what the formula is, because it's really, really important that you know what the formula is. And don't try to always just take it step by step. Don't skip steps in this thing, because you will not get the correct answer. Because if you skip steps, it's just not going to work out overall. So what you will do is you will just write yn equals to yn h, so the amount of change times your dy dx, and then you want to count the number of steps before you substitute into the formula. Then you want to sub and just don't skip steps and just keep on going, right, until you get what you need. So you go y1, y2, y3, etc, etc. Good. Okay, so these are kind of some summary things for your things. So the fundamental theorem of calculus is going to be your x final, x initial, plus your y initial, because this gives you your amount of change that's happened. So the amount of change in your y that's happened from your final to your initial, right? So, and why this works is essentially because you think of FA, FB, f dash of x dx, right? That's going to be equal to FA minus FB, FB minus FA. So what that means is that this is going to be equivalent. So if you're trying to find FB, all you have to do is add FA in the end to kind of get rid of that. So you'll get that this is going to be your FB in that circumstance to actually get what the value is going to be. Good. Okay. So then in order to do separation of variables, this is kind of similar to your implicit differentiation. What you do is you organize all the y's on one side, organize all the x's on the other side, and then you have essentially y1, y0, whatever your function fy is going to be, dy is going to equal to your x1, x0, let's say g of x dx. So you just want to kind of organize it. And remember, you want to keep all the y's on one side and all the x's on one side, so you'll have to divide the y's across and kind of move the dx onto the other side. And then you put the plus c on the x side, and then you arrange so y is the subject in most circumstances. Unless you have something which is like a relation, like a circle or an ellipse or a hyperbola. In that case, you can probably just keep it in whatever kind of generic form they have. Okay, so in terms of growth and decay questions, they'll always say the words proportional, and just remember A is going to be your initial conditions and putting that in. Your k, or your variable, will be depending on whether it's growth and decay, and you have t will be equivalent to time. Your Newton's law of cooling, that's the kind of, when you anti-derive it, that's the value you're going to get. And then in terms of concentration and mixing problems, you're going to get that it's dq dv in, so the concentration in times the volume going in minus the concentration going out times the volume going out in terms of the question. For differential equations for slope fields, what you want to do is look at patterns and where things are going, and then you can look at shapes and where things are. For your graphs, you can kind of look at shapes and what it's going to look like. Euler's method makes sure organize your working out, and you can put this into your calculator to calculate what you need. Okay, so let's have a go at a question now. So we have the value of c, where c belongs to R, such that the curve is defined by y squared 3e to the power of t plus 1, and then, x plus 1, and then all over x plus 2, and that equals to c, and this has a gradient of 2 where x equals to 1. So they want us to find what the value of c is here. So what we can do here is we want to set up our equation. So we'll have that our fx squared will equal to this, right? And we'll kind of just set this up so we know where we're going. And what we want to know is, we want to know what the value of c is here. So we want to kind of substitute this in to be able to find out what's going on. So we're going to say that our 2, right, times our f dash of x plus f of x is going to be plus this, right? So we're trying to find out what is going on in terms of our function and where it's going, right? So then we can kind of substitute that in. So we'll have our function being multiplied here. So we'll have differentiation of the first part, which is going to be our y squared, so dy dx, times our x, right? So times our y, because that will just be 2y, right? And then we add a dy dx at the end, so it'll be 2y times our dy dx, which is our f dash x, and then we'll diff the second component. So we'll get that this is x minus 2 times our 3e to the x minus 1, right? Which is going to be our first component, and then we're going to do the second part of the question rule, which is diff the bottom and then keep the top. So that's going to just be that it's going to be negative, it's going to just be 1, right? Because x minus 2 diffed is just 1, and then times 3e to the x minus 1, and then that's going to be all over x minus 2 all squared, right? Okay, so then what we want to do is then rearrange this to get us what we need. So we'll have that this is 2 times dy dx plus times y will equal to our function, and we're going to be rearranging for what our dy dx is. So we're going to let our x equal to 1 and our dy dx equal to 2 at that point to give us what we need, and then we're going to do is substitute that in to get us our value, right? Because it wants us to find where that value is. So it wants us to find the value of c, where this is defined, and it has a gradient of 2 when y equals to 1. X equals to 1. So we're trying to find what the y value is so we can substitute it in to actually get this. So what we're going to do here is we'll have 2 times 2, right? Because that's our derivative, times y will equal to this. So we'll get our function there, right? So we'll get that our kind of value here will be 3 times our 1 minus 2, so that's x. So x is equal to 1, so 1 minus 2 times e1 minus 1 minus 3e1 minus 1. So, and then that'll all be over 1 minus 2, right? So 1 minus 1 is just e to the power of 0, and that's just 1. And we'll have 1, essentially negative 1 here, to 3 times negative 1 here, and then we'll have negative 3 here, times that, and then we'll have 4y on the outside, right? 4y plus, because it was 2 times y. And then that will all be over negative 1 squared. So this will all amount to 3 times negative 1 times 1, right? In terms of, because e to the power of 0 is just 1, and that's minus 3 times 1, right? And that's all over just 1. So all we'll get is, all in all, will be negative 3 minus negative 3 will equal to negative 4. So therefore we will get that y, right? Y will equal just 3 over 2, or 6 over 4, or negative 6 over negative 4. Okay, so then we have to substitute all back in. and we'll get that y squared plus our equation equal to c in the first place. So we now need to substitute what our y is. So we'll have x equals to 1 and y equals to 3 on 2. And when we substitute that in, we'll get it's 3 on 2 squared plus 3e to the 1 minus 1 over 1 minus 2. And then what we'll get here is that will be 9 on 4, and then 3 times 1 over negative 1, which will give us that will be 9 on 4 plus negative 12 on 4, because that's just 3. So all we'll get is that's going to be negative 3 on 4. And you can see that this question was done reasonably well. Most students recognize that you had to do implicit diff, but you can see that's quite a long question. It involved a little bit of working out and thinking. Okay, so next we're going to talk about this little tank here. So this tank had an initial 15 kilograms of salt dissolved in 100 liters of water. A solution of 1 on 60 kilograms of salt per liter flowed into the tank of a rate of 20 liters per minute. The solution of salt and water, which is kept in uniform by stirring, flows out of the tank at a rate of 10 liters per minute. So it wants y. If y kilograms is the amount of salt in the tank, write down an expression for the concentration in kilograms per liter of the salt at time t. Okay, so that's what we're going to do here. So what we want to do is we want to set the equation up and kind of figure out what we're looking for. So we're looking for the concentration, and concentration just equals to mass over volume. And what that's going to be for us is just y, and the volume at time t is going to be 100, and 20 minus 10, because that's the amount going in and the amount coming out. So our volume for kind of this is going to be our like outflow concentration, and that's always going to equal to the mass of the tank, so Q or whatever, over your volume minus your volume change, and that's going to be essentially minus 20. So it's going to be, you can, yeah, actually it would be, let's say plus volume change, depending on which way you want to do it really, but essentially, so it'll be 20 in and then 10 out, so then it will just be plus 10t. So we'll get that it's y over 100 plus 10t. And they want us to show that differential equation, kind of relaying this is equal to this. So what we want to do is we want our dy dt to be inflow minus outflow, and we can just set that up. So our inflow will be our 1 on 60, right, times our 20, because that's our concentration going in, and that's our kind of amount, our volume going in. So concentration times volume is going to be your mass. So you'll get that it's 1 on 3 kilograms per minute. And then your outflow, we already know what the concentration of the outflow is, which is y over 100 plus 10t. And then we'll just times that by the outflow out to give us that mass flowing out, which is 1 on 10 plus t, because essentially the 100 and 10 plus t kind of cancel out with the 10 there. And then we kind of put that all together. So we'll have that it's 1/3 minus 1 over 10 plus t, right? Okay, so then we want to kind of amount this all together to prove that it's equivalent to that. So we'll have that dy dt plus 1 over 10 plus t will equal to 1/3, right? And remember that our y was equivalent to 100 plus 10t in the first place. So we can kind of just replace that with what we have from there. So we'll notice that we can just replace that variable that we have down there with our function, right? To give us what we need, and that will be equivalent to having that there. So remember, this was y over 10 plus t, so we'll have y there, and then we'll have our y being there, and then our y will kind of transfer over there as well. We can see that we've proven the equation we want. Okay, so this one has a fish water tank of salt 4 kilograms dissolved in 100 liters, and it's decided that the concentration is too high, so that fresh water is mixed in at 10 liters per minute. So fresh water, it has a concentration of 0. So we have concentration of 0, so that means that the rate in will be 0 automatically, and 10 liters is being removed out, right? So that means that the volume is actually not changing, because the volume coming in and the volume coming out is the same. And it wants x as our kind of our value for our amount of salt, or our concentration. So dx dt is going to equal to the rate of change of our concentration, and our volume is 100 plus 10t minus 10t, which is 100. So 100 times dx dt is going to be the change in our mass, right? Because that's going to be the amount that's going to be coming out overall, right? Because dx dt is going to be, that's the change in our mass, because that's the change in our volume essentially. So 100 dx dt will equal to rate in times rate out, and that will be 0 minus rate out. So what we'll get here is our rate out will equal to concentration times rate outflow, which is going to just be x times our 10, because x was our concentration, right? So therefore we'll get this is going to be equal to kind of negative 10x in terms of our rate of change of our mass. So we'll get that 100 dx dt will equal to negative 10x, so therefore 10 dx dt plus x will just equal to 0 when we kind of rearrange and solve for that. So it'll be option A. Okay, so let's talk about this number of mobile phones now. So number of phones owned by a certain community after t years can be modeled by that equation of log e n 6 minus 3 e to the negative 0.4 t, and we have log e n equals to 6 minus 3 e to the negative 4t, and that satisfies that differential equation. And essentially it just wants us to kind of use this mathematical model to find the limiting number of mobile phones. So how we find the limiting mobile phones is we can find it two ways. We can either say that as t approaches infinity, log e n will approach 6, right? Because we can think log e n is going to, as this approaches infinity, this is going to approach 0, so log e n will approach 6. Or alternatively, we can say dn dt, we want the rate of change to equal to 0, so when it's no longer changing, and then we can just solve from there. So we'll have 0.4 times n will equal to negative 2.4, right? And that's what we want because we're essentially substituting this equaling to 0. So we'll have log e n will also equal to 6 when we kind of divide across. So therefore n will just equal to e to the power of 6, which is approximately 403. Okay, so sometimes you're asked to find the values of t, so make sure the values of t that you find are positive, and that's the main thing with finding solutions in general, that you must always check that the solutions you find are actually possible. So what you're going to do here is we're going to label a couple things. So we'll have that our kind of vector for that is going to equal to 7.5t minus 5 on 3 cos pi t over 6 j, because that's going to be our accelerate or our velocity, right? Because that's our position. So our velocity is just going to be kept by diffing that. So the t disappears and that will just disappear as well. And we'll have pi on 6 times our 10, which is going to just give us this value, so pi over there. And then what we'll get is that RT will equal to our 5 over 18, and this should have a pi in it, sorry, this should have a pi squared as well, in terms of kind of timesing out our variable there. And then what we'll get from there is that if we kind of substitute that equaling to 0, so the 5 over pi, the 5 pi squared will disappear into nothingness, and we'll just be solving for sine pi t over 6 equals to 0. So therefore our pi t over 6 will equal to n pi, because it can equal to any n pi, where n belongs to z. We're doing a bit of a general solution here. So then we can try solving for that, and we'll get that t equals to 6n, where n belongs to z, because we've divided everything by pi and times it by 6. And then so what we will have here is that that's a kind of general solution that we'll be able to have. And the key thing here is that you need to make sure that the things that you have are positive, right? But how we've done that is put a z plus here. So we made sure that n is bigger than 0, and that time, so it could be kind of including 0 as well, because the time equaling to 0, but we need to make sure that it's positive, so that's why we had to do that. So you couldn't just say n equals to z, because then that would be a negative time there. Okay, cool. So Euler's formula, how we do this is we need to just substitute into the formula. So what we're going to do is we can build a table here. So our x0 equals to 0 and our y0 equals to 1 as given by the formula. Then our x1 is going to equal just x plus h, which is 0 plus 0.1, which is just 0.1. Then we substitute into the formula. So y1 equals to y0 times h times fx x0. So it'll be 1, right, plus 0.1 times our h times our dy dx at 0, which is cos 0, which will just, cos 0 is just 1, so it'll just give us 1.1. Then we find the next one, so our next one is for when x equals 0.2, and that's going to be, once again, we kind of substitute it in, so it'll be 1 plus 1 from the previous one, times 0.1, and now cos 0.1, because that's now, we need to substitute in our cos x1. right? It's kind of going up in ratio if you think of drawing like little mini lines to get to where we need. And then when we substitute that in, we'll get that that's just going to be 1.195, etc. So that's going to correlate with our function there, and that's what's going to give us our function overall. And then if you kind of, have a go at doing this part of it, because it's asking whether it's an overestimation or underestimation. So all we have to do is anti-diff it, and when we anti-diff it, we'll get y equals to sine x plus c, and we need the constant of integration. Then we substitute that in to get us our value. So we'll just get that y equals sine x plus 1, and we sub in 0.2 to get us y2, and that will just equate to 1.19 something. And you can see here that it's 1.19, and the difference is 1.198 and 1.199. So you can see that's an overestimation. So it'll be part B, or answer B, more like. Okay, so this is a question which is about solids of revolution. So all we need to do here is substitute into the formula. Always just put the formula down first for this type of question. And because it's rotated around the x-axis, don't need to rearrange the formula, and all we have to do is substitute this in, and we'll just give us x squared over x squared minus 4 from 4 to 3, so our kind of terminals. And the denominator is a reducible quadratic, so we can use partial fractions to simplify this. But because the degree of the numerator is the same, we can also just use our knowledge of functions in general to kind of rearrange this, and then use partial fractions to simplify it. So what we'll get is x squared over x squared minus 4. We can kind of change that. So what I like to do is match the denominator with the numerator, which is what they've done here. So x squared minus 4 and then x squared minus 4. And then you think about the amount that's changed. So that's just the plus 4 at the top. So we'll get that. It's 1 plus 4 over x minus 2. X minus 4. So now you need to use partial fractions to kind of change that. So you'll get 1 plus 4 over x squared minus 4 will equal to 1 plus 1 over x minus 2 minus 1 over x minus 2. Essentially, you just sum them into partial fractions to find that. And then we can anti-diff it. So we'll get that the first one anti-diffs to x, and the second part anti-diffs to log e x minus 2, and the third part anti-diffs to negative log e x minus 2, so we can combine the logs together to give us x minus 2 over x plus 2, and then we substitute all of that in, and we can put the pi out to the front. So when we substitute that in, we'll get that's going to be 4 log e 4 minus 2, which is 2, and then 4 plus 2, which is 6, so we'll have that it's 2 over 6, so it will be 4 plus log e 1 on 3, and then minus, we'll have 3, right, minus log e 3 over minus 2, which is just 1, and then 3 plus 2, which is 5, so we'll have 1/5, so we'll have 4 minus 1, which is 4 minus 3, which is 1, and then we'll have log e 1/3 minus log e 1/5, which turns out to be plus log e 5, so all in all we'll just get pi 1 plus log e 5 on 3. Great, and that's what we get in that option there. Okay, so in terms of integration techniques, we kind of talked about whether it's smaller than, bigger than. So if it's smaller than that function, use partial fractions. If it's equal, then break it up and then use partial fractions. If it's bigger than, then break it up and then use long division and then use partial fractions to get what we need. So if you don't know the integration technique, just ask yourself a couple of questions. 1, is there a derivative for a similar function, right? Integration by recognition. 2, can I use double angle or kind of simplification, so tricks? Can I use the derivative of the inner function, so substitution? Is there a quotient function, or does it have like a reducible quadratic in the equation? And then partial fractions. Is the quotient function, or does it have an irreducible quadratic in the denominator? And then linear substitution or inverse trick to find what it is. Or is there a quotient function, or does the function have a square root in the denominator? Then it's inverse trick. And in the first bit, you'll always notice that you're talking about integration by recognition, and the key thing here is that you can absolutely, for a lot of the functions, use integration by parts as long as you have two functions being multiplied together, and that's a key thing that you can recognize as well. Good. So if we look at this, which function should we use? So we can kind of screen through the techniques. So is there a similar function in what we have, right? Not really. Can I simplify using double angle? Not really. Trick, right? Is the function being multiplied by the derivative of the inner function? Yes, because we can see that we have x cubed here, and we have like kind of similar things going on there. So we can see that it's going to be integration by substitution to get what we want here, because we have x to the power 5 here, and we have x to the power 4, or 5x to the power 4, which is even more perfect, because that's exactly the derivative of x to the power 5. Good. So what we want to do is we can kind of put that in. So we'll say that u equals x to the power 5, so du dx equals to 5x to the power 4, and then we can substitute that in to get our function. So we'll get kind of put that in to get out in terms of du, and we'll just end up with 1 integration of 1 minus e to the power of u du, which just integrates to u eu plus c, and then we can substitute the kind of x back to, so it will just be x to the power of 5, and then minus e to the power of x plus to the power of 5, and then plus c at the end. Good. Okay, so with this one, screen through the techniques again. So not really a similar function, not trig, not really the derivative of the inner function, right? Because that would be negative 2x. Is it a quotient function? Yes. So it does it have a reducible quadratic? Not really. Does it have an irreducible quadratic? Once again, not really. Does it have a square root? Yes, it does have a square root. So we want to think about what we want to do here. So we want to kind of change this into two components, right? Because this part is going to be the square root component, and this part is going to be the derivative of the inner function, right? So we split it into two parts, so it kind of gives us two components to it. So what we want to do here is kind of split that into two parts and then kind of integrate them separately. So this will directly integrate just to the sine inverse function, and then what we want to do with this part is do a bit of substitution. So we'll say u equals to x squared, so du dx will just equal to 2x, so dx du will equal to 1 over 2x, so we'll get that that's going to be the function. So we'll have that this is going to be x times root 1 minus u, which is 1 over 2x, to get you the du here, so that you can substitute the du dx into it. Also, I sometimes just like to replace this with du dx, and I find that's pretty simplistic as well. So if I made this into 2 and then kind of put a half there and just replaced it, that's also fine as well. So then you times it by, so what you'll get is 1 over root 1 minus u times a half, right, to get you your function, and that's going to anti-diff to, you can take that half out to the front, and then that's going to anti-diff to essentially putting the half to the top and then dividing it by a half and dividing by negative a half, I should say, to get you your function, because of the negative 1 there, and then dividing by a half because you've raised it. So all in all, you end up with 2 sine inverse x minus root of 1 minus x squared plus c. Good. Okay. So this one, right away, we can tell it's a trig. So let's kind of get started with this. So because we know it's a trig, what we can do is we can substitute in our function here to get us what we need. So we'll have that this is going to be sine squared x cos squared x. And what we want to do is we first want to rearrange this so we have one of the kind of trigs by itself. So we just want to leave it with cos in the middle. Then what we can do is now we'll have just cos x sine squared x minus sine to the power 4x, and we can do the substitution. So we'll sub in that u equals to sine x because cos by itself. So then we can get du dx equals to cos x, and then we can substitute the du dx directly for that position. So we'll get rid of the x essentially component, the dx component. And we'll just end up with u squared minus u to the power 4 du, which anti-diffs to, if we raise the power by 1, we'll get u cubed over 3, and then raise the power by 1 again, we'll get u to the power 5 over 5. So then we can substitute it back in to get sine cubed x over 3 minus sine to the power 5 over 5 plus c. Good. Alright, so with this one, we want to find diff this, hence do that. And right away, it's going to be integration by recognition question. So first, they've asked us to already diff it, so we already know what the derivative is. So then we're going to integrate the derivative that we already have. So we know that this 3x tan inverse 2x is going to be the antiderivative of the derivative we just found, which is 3 tan inverse 2x plus 6x over 1 plus 4x squared. Great. So now we can kind of split that up into two components to get which part we want. And we want this first component here. So we're going to move that to the other side to give us what we want, right? Because we're going to move this to the other side so that we have only our 3 inverse tan inverse 2x on this side, because that's the function we want. And then we've already found what the function we want is, so we can clean up the kind of this side here. So we'll have u equals to x squared, and then we'll have du dx will equal to 2x, and then dx du equals to 1 over 2x. Alternatively, you can also do here, rather than doing that, you can also make this equal to u equals to 1 plus 4x squared as well, and that way you can substitute the bottom directly equaling to u, and then your du dx is just going to equal to 8x. So it's kind of up to you which substitution you do. So then you'll get 3, the function that we want will equal to the original function we started with, times 6x 1 over 4 plus u times 1 over 2x, and that's going to just end up to be 3 over 1 plus 4u du, right? Because this turns it into du dx, or turns that into du to get what we want. And then we can just anti-diff that and find what we need. So we'll get that that's going to be 3 on 4 log 1 plus 4u plus c. Then we substitute the u back in to get our function, and we can kind of divide the 3 across if we didn't want it, and we can also keep the 3 if we needed it in this function because it wants it in that one, and then we substitute it back in at the end. So we'll substitute the u back in at the end to give that this is going to just be equivalent to x tan, so it will be this line that we want, so 3x tan inverse 2x minus 3 over 4 log e 1 plus 4x squared plus c. Great. So for this one, we can see that we've got our kind of substitution here. So what we want to do is we kind of screen through the options here, and we can see that it fits with, is there a function being multiplied by the derivative of the inner function or something similar, right? So we can kind of use that. And so what we're going to have here is we can say let u equal to a half x minus 3, so x will equal to u plus 2u plus 6, right? So du dx will equal to 2. So we can use that to our advantage, and we use our du dx as 2, or dx du as 2 to get rid of our kind of x component, so that we only end up with a u component here, or that we kind of, so essentially what we do is we split this into kind of dx du times du, to get rid of that dx component. So we split it into 2 parts. So we need to multiply it by our dx du, which is multiplying everything by 2, and then we convert everything else to kind of u. So our 2x will just turn into 2 times 2u plus 6, and then we convert everything to u, and then we can kind of expand it to give us our values that we can therefore anti-diff more easily. So we'll get that this is going to be u to the power of 3 on 2 plus 6 u to the power of a half. So when we kind of anti-diff that, we'll raise the power by 1 and divide by the powers, which will give us 4 times that. And then we can substitute everything back in. So we'll end up with the final function being 16 over 5 a half x minus 3 to the power of 5 on 2 plus 16 a half x to the power minus 3 to the power of 3 on 2 plus c. Okay, so in terms of vectors, so a couple kind of little things that you want to have in your formula sheet though. So the magnitude of the vector, that's just going to be kind of based on the Pythag theorem. Parallel vectors, what you want is one to be the ratio of the other, and unit vectors, it's just going to be divided by its magnitude, because we're trying to make the magnitude 1, because it should solely just talk about a direction. So in terms of what we're having here, a dot product is just the two functions being multiplied together, and there's 2 ways to represent it. So this is the first way to represent it, and the second way to represent it is like this, and that's used to find the angles, and that's because our other way to represent our kind of dot product between 2 functions is just modulus A times modulus B cos theta, and that's actually derived from the cosine rule in terms of what our function is. Good. Alright, so in terms important properties, if you times the function by itself, it's just equal to the magnitude squared, and that kind of makes sense because a times a, you just times it by, you just collect the I terms and collect the j terms and multiply them. If they are equaling to 0, if we multiply, those 2 vectors are perpendicular, and that's because really if they were non-zero vectors, the only thing that could equal to 0 is cos theta, and cos theta equals to 0 at 90 degrees. Okay, in terms of vector projections and vector resolutes, so if you have wood floor, you're looking for the shadow of the wood on the floor, right? So A in the projection of B. So if you have a sun here and you think of the shadow that it casts here, that's exactly what we're going to be doing. So we're thinking about the shadow and also kind of the vertical component. So W and U, so U is going to be the A parallel to B, and W is going to be the A perpendicular to B. And to find those, we just essentially talk about the components of A. and they like to talk about shortest distances using this. So if we have something like that, that's normally what they talk about. Okay, so kinematics, the main things that you have to know are the definitions. They like to use VT graphs a lot because they can represent, so area represents a displacement or distance, the coordinate represents the speed or velocity, and then the gradient represents acceleration. So that's why they like to use it. The difference between these is you have vector and it's kind of scalar equivalents of most things, except for acceleration. You can talk about it as a vector or a scalar, but displacement is going to be your signed area under your curve, whereas distance is going to be total area under your curve, and that's because your distance is going to be your magnitude. It's magnitude based or a scalar base. So x is going to be your position and v is going to be your velocity. So to get from one thing to another in terms of where you're getting, you're going to be thinking about diffing to get from x to v to a, you're going to be diffing, and then to get from the other way around, you're going to be anti-diffing to kind of get the other way around. So that's a relationship between your displacement, your velocity, and acceleration. In terms of velocity, different ways you can represent it. So average velocity, it's just going to be the change in position over time. Instantaneous velocity is going to be the derivative, and you can talk about it as just the velocity. And average speed, you have to actually calculate the area under the curve and then divide it by the time. Units is always meters per second unless they specify it, and if they have kilometers per hour, you can divide it by 3.6 to get it back to meters per second. In terms of acceleration, it can be represented just by v2 minus v1 over time. If you're averaging, then instantaneous acceleration is just going to be a. And remember, motion direction does not equal to acceleration, so your motion direction is going to equal to your velocity. So it can be moving to the right but slowing down, so i.e. acceleration is actually moving to the left. Constant acceleration formulas. You must know these. These are really, really, really helpful, and it kind of helps you avoid doing integration. If you have an unchanging or a constant acceleration, you can use these both for scalar things and for vectors. Okay. If you have projectile motion, mostly Savat, unless they tell you that there's like air resistance. So normally horizontal, there's no acceleration unless stated. So normally they just throw straight up, and speed is always constant unless there's air resistance. And if there's air resistance and the air resistance isn't constant, that means that you can't really use the Savat equations. And the vertical, you'll have gravity, and normally they'll tell you what gravity is equivalent to, whether it's 10 or 9.8. These are some equations that you can use for acceleration. They're really helpful for multiple choice questions, and they love using this one. So v equals dv over dx, and that's because v is dx over dt, so it kind of cancels out to dv dt, which is what acceleration is. But you must know when to use this and where to use this. So if you have ft, you can just use dv dt. If you have a equals to v, you just do the flipping of the variables to get what that is. If you have a equals to fv or fx, what you can use is v dv dx, and similarly you would use that for that type of situation, but it's really important that you know which one you're using. Good. Okay, so let's go through kind of a bit of a question now. So acceleration equals to meters per second of a body moving in a straight line in terms of velocity, and a is given by 4v squared. So given that v equals to e when x equals to 1, where x is the displacement, find the velocity of the body when x equals to 2. So what you can do here is use a equals v dv dx, because you've got v and you've got your x, right? So that's what you want to use. So you'll get that v dv dx equals to 4v squared, so you'll get dv dx will equal to 4v, and then you can kind of flip that to get you dx dv equals 1 on 4v, so you're integrating based on v, and then you'll have integral of 1 over 4v will just equal to a fourth log ev plus c. Then you can substitute in v equals to e when x equals to 1, so you'll have 1 equals to log e plus c, so c will equal to 1 minus 1/4, so c will equal to 3 on 4, because log e is just 1, and then you'll get that x will equal to 1/4 log ev 3 on 4, and you can technically just kind of remove this because your velocity is always going to be greater than 0, but we can keep it for now. So then you substitute in when x equals to 2, right? Or you can kind of rearrange for it. So we can rearrange here to kind of get v equals to e to the power of 4x minus 3, right? And or we could just substitute when x equals to 2. Then you can let x equals to 2, substitute that in. So you'll get that e equals to 4 times 2 minus 3, which will mean that v equals to e to the power 5. So you'll get that e to the power 5 meters per second. If you're working with vectors, it works the same way. So what you're doing is you're just considering each dimension separately, and it works the same way to go from your position to your velocity to your acceleration. Good. Okay, so these are some formulas that you can use. So if you're finding the total distance traveled, all you have to do is root the whole equation, because remember, if we're talking about magnitudes in our vectors, all we had to do was kind of square each individual component. Distance between the object is just the magnitude of the two vectors minus each other. And then the direction of motion is always given by the velocity. This is the important thing. So crossing paths is they share the x point, but not necessarily the time, whereas colliding, they have the same time at the same point. So that means that the x and the y components need to both equal at the same t. And this is kind of the thing of, if you're at the same point at the exact same time, you collide, but if you just cross paths, you might not collide. And how you find the first part about crossing paths is you just get the two equations, solve for them, and just make sure that it fits within the domain for t. For these ones, in terms of shortest distance, what you're going to be doing is you're going to be finding the perpendicular distance, right? Because remember, your perpendicular thing is going to tell you where that's going to, when that vectors, 2 multiplies vectors multiply to 0, that's going to tell you when it's perpendicular. So all you really want is for the velocity equation times that equation to equal to 0, because your velocity equation is going to give you the direction of motion of the curve. So the steps is to convert the point to a vector, subtract the curve from the vector, multiply the vector, and then let the dot product equal to 0. So if we kind of go through this example here, what we want to do is they want us to find the shortest distance from origin when t equals to 2, given that r0 equals to 1 minus 2k. So what we want to do here is we'll have r will equal to 2t squared minus 3ti plus t squared j minus 5tk, and that's by substituting this into kind of anti-differentiating, and then we'll have a plus c. So when we substitute the plus c into it, what that will mean is when we kind of rewrite this to get what c equals to, we'll get that c equals to 1 minus 2k. Then we can substitute that back into the formula to give us our r equation overall. And now we want the distance from the origin, so that's going to be the distance from origin equation, because it's from origin, so we don't need to minus anything from it. And then we just times it by our kind of vector, or we times it by our velocity to give us the distance of the particle from the origin. So r2 will equal to 3i plus 4j minus 12k, and then we just kind of modulate that to give us our distance. Okay. So kinematics, the biggest tip is just draw everything that you're involved in, and you're not really asked to do this anymore, but I thought I'd just include it as kind of a bit of information about some application questions you might be asked. So in terms of Newton's law of motion, you don't strictly have to know them anymore, but the first law of motion is about inertia, the second law is F equals ma, which is probably the one that's most important and that will come up the most, and the third law of motion is that everything has an equal and opposite reaction. And we have this is essentially all the different weights, and now in the study design, because it's no longer formally part of the study design, you should get told what each of these really mean. But I think having at the back of your mind that F equals to ma is good, and also acceleration approximately equals to 9.8 downwards is also important. Okay, last couple little things. So in terms of your exams this year, I'm sure you've already got your exam timetables, but just make sure you're aware of when they are and plan your study accordingly. In terms of bound reference, try to finish your bound reference before doing practice exams, and it can be as messy as you like, as long as it works for you. That's what's most important. So make sure to put all your formulas, calculated commands, and everything in before you start practice exams, or whilst you're doing practice exams, and kind of build up your bound reference as you go. And you don't need, like, a small bound reference, a large bound reference, doesn't really matter, as long as you can find where you're going. Make sure to do practice exams as much as possible. I recommend MAV, NEEP, VCA, and the NHT VCA. Probably do company exams first, and then once you get closer to exams, do the VCA exams. But you can do older VCA exams, then older company exams, then older VCA exams, then company exams more recent, and then kind of more recent VCA exams to kind of build up, and make sure you know which parts of the study design are no longer applicable, and try to get your teacher to give you some papers, because VCE is school versus school, and make sure to help each other out in terms of questions, and correct yourself harshly, and this applies both for maths and all other subjects as well, and make sure to analyze your performance. Before the night, make sure to go sleep early, eat well on the day to make sure you have the energy. Make sure you're comfortable with your calculator and have a spare calculator. Teaching is often a good way to learn concepts, and I found if I taught somebody something, I would kind of remember it better. So make sure. And just the day before, do not cram, do not try and cram all the knowledge, because really the amount you know will be the amount you know. Like, the amount you know the day before will be, no matter how much you cram, will be the amount you know on the day of the exam. So just kind of try to study consistently rather than cram. So exam one advice: use your reading time wisely and make sure to form a plan of attack. So do what you need to do first. So managing your time is the main thing in exam one. And just move on questions. Kind of, if there's questions you can't do, just move on and you come back. Each mark is worth the same number of marks. Exam two, once again, try to use reading time wisely. Use it to read the extended response first, right? And then what I like to do is I like to do a couple multiple choice in the reading time as well, and I found that helped me manage my time better. And with multiple choice, because you can always guess, it's probably smart to do extended response first. But see which one works better for you when you're doing exams. And make sure you're comfortable with using your calculator, and make a new problem time for every question, and make sure you define every function that you're working with. Okay, just do whatever you like, and essentially just build up your experience from doing practice exams. And from doing a practice exams, you'll figure out what you like best. Make sure to draw, underline, and check, okay? Checking is really important, checking that you have the correct units, correct form, you've answered the question, and that all your answers fit within the domains. Draw if you need to, if you're confused, or if you want to just have an equation. Underline, highlight, do whatever you need to there, and I found that really helped me kind of limit the amount of silly mistakes I made. Always give your answers in exact form unless asked otherwise, and just kind of keep that in mind. And once you're done the exam, just I remember panicking in one of my exams, and just remember, have some water, take a breath, and that's what's most important, because if you freak out, you won't be able to really do anything. So just make sure to also practice your practice exams in a really strict exam environment, and that will stimulate it so that you're kind of a bit desensitized to it. And then kind of during exam season, make sure to take time off and make sure to relieve your kind of stress by making sure you have time to do breaks. Okay, so we have a TikTok, so have a look at that if you're interested. It has lots of study tips and all of that. And that comes to the end of our lesson today. So make sure to study smarter and study consistently and study in blocks, and good luck for all your exams.